Hello, here is an example for maximum power transfer theorem. We had to determine the maximum power delivered to the load RL for the circuit shown below. This is a circuit in which we have a single voltage source and some resistances, and the load resistance RL, which is indicated as variable, and corresponding resistance is not given. We have to find the corresponding load resistance, and then we have to determine the maximum power delivered at the resistor RL. Okay, right, that is the question here. You have to find the value of RL and the power delivered at RL from the source. So let me redraw the circuit, and I will be back to you after that. Okay, let us mark these points A and B, and I'm going to find, or I'm going to convert this circuit to the left of AB. Okay, I'm going to convert the circuit to the left of AB, left hand part of the circuit, excluding the resistance RL, into a single voltage source and a series resistance. Okay, in order to solve this question, I have to convert this circuit in this form: a single voltage source, say V, and a resistance R, say Vs and Rs, followed by this load resistance. Okay, then only we can solve this question, because in the topic under maximum power transfer theorem, we discussed that the maximum power will be delivered to the load resistance only if the source resistance and load resistance are equal. If R is equal to RL, maximum power will be delivered here. But we have a single voltage source and a combination of four resistances are here, excluding RL. Okay, so we have to convert this circuit except this RL in the form of a series voltage source and a series resistance. Then we have to connect the load resistor back and solve for the question given. Okay, right. So first of all, I'm going to convert this circuit, this portion only. Okay, I'm going to convert this circuit into a single voltage source and a series resistance. How can we find that? Here is a theorem. Just we have discussed in our previous videos. Any circuit containing more number of voltage sources, current sources, resistances, etc., that can be converted into a single voltage source and a single current source. A circuit having large number of voltage sources, current sources, resistances, etc., can be replaced using a single voltage source and a single series resistance using a theorem known as Thevenin's theorem. So we have to find the Thevenin equivalent circuit for the circuit highlighted here. Okay, right. Okay, so we have to find the Thevenin equivalent circuit of a circuit across AB. Okay, in order to find the Thevenin equivalent, we have to find the open circuit voltage across AB, that is VAB, and the resistance, equivalent resistance across AB, that is RAB. That will be Thevenin voltage, and this one will be the equivalent resistance across here, will be the Thevenin resistance RTH. Okay, VTH and RTH. So we have to find, first of all, let us find the voltage across the source, across AB, that is VAB. VAB will be the voltage across 3 ohm. Now find the Thevenin equivalent voltage across AB, that will be equal to V3 ohm, that will be VTH. Okay, voltage across 3 ohm current, 3 ohm resistance. How can we find that? By any means we can find them, and let us move through a simple way. The voltage across here will be the product of simply V is equal to I into R. Therefore, voltage developed across the resistance 3 ohm will be the current flowing through 3 ohm resistance into 3 ohm. That will be the voltage developed. So, I need to know what is the current flowing through 3 ohm. Okay. So, I'm going to find the total current supplied by this 50 volt voltage source. In order to find the current through 3 ohm resistance, we should know the total current provided by the 50 volt voltage source. Means the total current IT. Okay, that current IT upon reaching here will split into two, and a portion will flow through 5 ohm resistance and another portion will flow through 2 ohm resistance. Then that will develop a voltage across 3 ohm resistance. That is what we are going to find. So first of all, let us find the total current supplied by the 50 volt voltage source. For that purpose, let us evaluate the equivalent resistance across point C, D. I am marking a point C and D, and now I am going to find the resistance across CD. Okay, total resistance across CD. Okay, now we are going to find the resistance across terminals C and D, RCD. For that purpose, I have redrawn the circuit once again by simply neglecting the terminals A and B. Okay, just we are going to find the total resistance. Okay, so let us try to find the relationship between these resistances. What about this 2 ohm resistance and 3 ohm resistance? They are in series with each other. Then corresponding equivalent resistance will be, if two resistances R1 and R2 are connected in series, then total resistance will be R1 and R2. Okay, all of you know that. Hence, let us redraw the circuit by simply replacing this series resistance with the corresponding resistances. Okay, this is point C and 10 ohm resistance, then 5 ohm resistance, and now I am going to replace replace these two series resistances with the corresponding equivalent resistance. 2 and 3 are parallel, therefore total will be 2 plus 3 gives 5 ohm resistance. Okay, right. Now let us complete the circuit. Okay, C and this is D, and we have to evaluate CD. Okay, right. Now take a look at this new circuit. What about this 5 ohm and 5 ohm? They are parallel to each other. Therefore, we can again replace these two 5 ohm resistances by corresponding equivalent circuit. If two resistances R1 and R2 are parallel, okay, then equivalent resistance will be equivalent resistance will be R1 R2 divided by R1 plus R2. Let us apply this concept. So let us again redraw this circuit. C, then resistance 10 ohm, then the parallel combination of 5 ohm parallel to 5 ohm. Okay, right. Then this is D, and we have to find RCD again. What about this calculation? 5 ohm and 5 ohm, that will be by using this formula, 5 into 5 divided by 5 plus 5. Okay, that will be equal to 2.5 ohm. Okay, right. Now, what about the equivalent resistance across C and D? This 10 ohm and this 2.5. This is 2.5 ohm. What about their relationship? 10 ohm and 2.5 ohm are series are connected in series. Okay, then RCD will be 10 ohm plus 2.5 ohm, and the corresponding resistance will be 12.5 ohm. Okay, right. Now we got the resistance across here as 12.5. Okay. Now we have a voltage source equal to 50 and total load, total resistance connected to the voltage source is now we obtained as 12.5. Then we can find the current, total current I. Didn't you get me? Okay, I will explain once again. Okay, now the total current IT. What is the total current in our circuit? Its location. This is IT. Okay, right. Total current IT supplied by this 50 volt voltage source. Again, simply by Ohm's law, I equal to V by R. That is potential drop divided by total resistance. What about the voltage supplied by this voltage source? That is 50 volt. Okay. Therefore, 50 divided by what about the total resistance? The total resistance connected to the 50 volt voltage source we obtained is the total resistance across C and D, that is RCD, that is obtained as 12.5. So divided by 12.5. So that will be the total current total current IT. Okay, right. That is equal to 4 ampere. Actually, our purpose is to find the current flowing through the 3 ohm resistance. For that purpose, we found the total current IT. Then IT is equal to 4 ampere. That is 4 ampere current. Upon reaching here, of course, that will split into two current components. A portion will flow through 5 ohm resistance and another portion will flow through this 2 ohm and 3 ohm resistance. Okay, now we have to find the current flowing through this branch only, 3 ohm. The current flowing through 3 ohm. Thereby we can find the voltage across 3 ohm resistance. That will be the VAB, that will be the Thevenin voltage. Okay, right. Okay, now let us find the current flowing through this 3 ohm resistance. The total current supplied by the voltage source we obtained is equal to 4 ampere. So to find the current flowing through the 3 ohm resistance, let us apply the current division rule. For that purpose, I am going to redraw the circuit excluding this voltage source and current source. That will make you to understand the concept more simply. Okay, this is 4 ampere. Okay, it's 4 ampere. And then followed by 5 ohm resistance, 2 ohm, 3 ohm, 5 ohm resistance, 2 ohm, 3 ohm. Then we need to find the current flowing through this branch. That will be exactly same as that of the current flowing through the 3 ohm resistance also. Okay, and let us denote it as I A, and this is let it be IB. Okay, simply take it as IB or I1 or I2, whatever it may be. Let us take it as I1 and I2. Then let us refresh the current division rule. Okay, this is current division rule. Suppose the total current is IT and that is we split it into two components, I1 and I2. Here we have two resistance R1 and R2. Okay, I1 is the current flowing through R1 and I2 is the current flowing through R2. Then by current division rule, I1 will be, this is I1, okay, in this direction, and the I2 in the downward direction. I1 is equal to total current into I1 is the current flowing through this resistance. Therefore, I1 will be equal to I total into the resistance opposite to R1 is equal to just R2 divided by total resistance in this loop. That is R1 plus R2. Then similarly, the current flowing through this resistance I2 will be again total resistance into the opposite, the resistance opposite to R2 is R1. Okay, R1 divided by total resistance R1 plus R2. This is basically the current division rule. Let us apply this formula in our case. Then we can find the current I1. That will be I1 is the current flowing through this loop. Okay, that will be equal to opposite resistance. The resistance opposite to this loop is this 5 ohm resistance. Okay, sorry, the total current is 4 to IT is equal to 4 ampere here, 4 into, okay, the current of, sorry, the resistance opposite to this branch is 5 ohm. 5 ohm divided by total resistance in this loop is this 5 plus this 2 plus this 3. Okay, that will be the current flowing through this branch, and the value obtained will be 2 ampere. Then we got the exactly the same current will flow through the 3 ohm resistance, and here we have A and B. Okay, right. Now we have to find VAB. VAB, that is the voltage across 3 ohm. V 3 ohm. Okay, that will be our Thevenin voltage, VTH. What is voltage developed across 3 ohm resistance? That is the current. That is the magnitude of the current flowing through to 3 ohm resistance, that we obtained it as 2 into corresponding resistance 3. Okay, 2 into 3. The voltage drop across here will be the product. Simply V is equal to I into R again. I is equal to, we obtained as 2 ampere, and corresponding resistance here is equal to 3. Okay, 3 into 2 gives 6 volt. 6 volt is the Thevenin equivalent voltage across A and B. Now let us write as Thevenin. Okay, now let us write it as Thevenin resistance across AB is equal to VAB is equal to V3 ohm is equal to VTH is equal to 6 volt, and just mark it as equation number 1. Next, in order to draw the Thevenin equivalent resistance, in order to draw the Thevenin circuit, we should need corresponding resistance also. VTH and RTH both are required to draw the Thevenin. So we have to find the resistance across, equivalent resistance across RAB. That is RAB is equal to RTH. We already discussed about that also. Okay, V Thevenin means voltage. R Thevenin means the equivalent resistance feeling across the terminals A and B. That will be equal to RTH. And now let us find RTH across AB. Okay. Okay, now let's find the resistance across A and B, that is RTH. Resistance across A and B in this circuit. Okay, I'm going to here is a problem here. Here, while calculating the equivalent resistance across AB, there is a voltage source is here. So we have to nullify this by short circuiting. Okay, just it will be difficult to find the equivalent resistance while voltage source is here. So we have to nullify its effect. If it is a voltage source, just short circuit it. If it is a current source, just open circuit it. Then voltage will be 0. Okay. In order to make a current source equal to 0, we have to open circuit it. Then current will be 0. Here we have to short circuit it. Then just to short circuit that, here CD, just simply replace the branch CD by using a short circuit. I am going to draw the corresponding circuit now. Okay. Okay, here I am going to replace the 50 volt voltage source across CD by using a short circuit. Not shown the 50 volt voltage source is here, as it is short circuited. Then 10 ohm, next this 2 ohm, then 5 ohm, and finally this 3 ohm, then A and B. Okay, right. Now we have to find the equivalent resistance across A and RAB, equivalent resistance across A and B. That will be the Thevenin equivalent resistance. Okay, right. That is what we are going to find here. Now let us start. We need to get the resistance across here. So let us start from the opposite side. What about this? What about the relationship between these two resistance, 5 ohm and 10 ohm? They are parallel to each other. Okay, right. Let us replace these two resistances by their corresponding resistance. Okay, corresponding equivalent resistance means 10 ohm and 5 ohm are parallel. So let us redraw the circuit as by let us replace these two resistance with their equivalent resistance. 10 ohm and 5 ohm are parallel. 10 ohm parallel 5 ohm. Okay, right. Then this 2 ohm resistance, then this 3 ohm resistance A B. Okay. What about 10 ohm and 5 ohm are parallel? That will be equal to 10 into 5 divided by 10 plus 5. Okay, that is equal to 3.33 ohm. Okay, 3.33. 10 ohm and 5 ohm. This 10 ohm and 5 ohm are parallel to each other. R1, R2. R1, R2 divided by R1 plus R2. R1, R2 divided by R1 plus R2. Okay. Now, let us find the relationship between this 3.33 and 2. What about the relation? They are connected in series. So let us replace these two resistances using their corresponding equivalent circuit. Okay, that is 2 ohm in series with 3 ohm. So 2 ohm plus 3.33 ohm gives 5.33 ohm. Then this point. Okay, right. And here we have a 3 ohm resistance. Then A and B. Then finally this 3 ohm resistance and 5.33 ohm are parallel. So let us replace these two parallel resistance with their corresponding equivalent resistance 5.33, okay, parallel with 3 ohm resistance 3, that is equal to 5.33 into 3 divided by 5.33 plus 3, that will be equal to 1.92 ohm. That is RAB is equal to RTH, that is equal to 1.92 ohm. Now we obtained both VTH and RTH. Now what we obtained is RTH is equal to 1.92 ohm. Okay. Let us mark it as equation number 1, and in the equation here in equation number 1 we have VTH, that is equal to 6 volt, that is the voltage across AB, and here also we have the RTH, that is equal to RAB, that is equal to 1.92. Now let us draw the Thevenin equivalent circuit across AB. Okay, let us draw the Thevenin equivalent resistance across here AB, RAB. Okay, this will be the Thevenin equivalent circuit. VTH we obtained is 6 volt by equation number 2, and by equation number 1, and RTH we obtained is 1.92 ohm by equation number 2. Okay, now let us connect the resistance RL, load resistance, which is given in our question. Okay, now we have a resistance given. Okay, we disconnected it in order to find the Thevenin equivalent circuit. Now we found the Thevenin equivalent circuit across AB. Now let's connect it back. Okay. Okay, this is the resultant circuit having only single voltage source, single resistance, and a load. Now let's apply the maximum power transfer theorem. by maximum power transfer theorem, we can say that maximum power will be delivered to this load only if this resistance and this resistance are equal. Okay, that is the statement. This is the circuit for maximum power transfer theorem. Suppose we have source resistance Rs and voltage source Vs and the load resistance is there. Okay, then maximum power will be delivered to this resistance only if source resistance Rs is equal to RL. In our case, maximum power will be transferred only if RL will be equal to RTH. Okay, right? That is equal to 1.92. Now I'm going to draw the corresponding circuit to find the maximum power delivered at load resistance. Okay, that was given in the question. Determine the maximum power delivered. Okay, right? So we have to evaluate the power delivered to this load resistance RL also. Okay, now I wrote the value magnitude of RL is equal to 1.92 itself, which is exactly same as that of the Thevenin resistance. Okay, next we have to evaluate the power. Power is equal to P is equal to I square into RL. That is the power developed across the load resistance. So in order to find the power developed here, we should know the current flowing through this resistance. Then how can we find the current flowing through this circuit? Let us denote it as I. Current I is equal to, simply by Ohm's law, V is equal to IR, then I is equal to, of course, potential difference divided by R. What about this potential difference here? That is equal to 6 volt divided by what is equivalent resistance or total resistance? That is 1.92 plus there are two resistances. Okay, 1.92. That will be equal to 1.56. So, okay, current is simply potential difference by total resistance. Potential difference is 6 volt and total resistance is 1.92 plus 1.92 gives the current flowing through the circuit is equal to 1.52. Now at last we are going to find the power delivered at the load resistor. Okay, power delivered to the load resistor RL is given by P is equal to I square RL. What about I? I is equal to 1.56 square RL. RL is equal to 1.92. That will give the result as 4.67. Then what about the unit of power? That is equal to, that is in watts. Okay, thank you.